No. All right, cool. So, one thing before we get started, today is the unified versus staff kickball game on the baseball field, starting at 5 o'clock. So come out and support a great group of kids and watch them probably beat us because they're going to be better at us. So, we are excited, though. It's going to be fun. I think the Special Olympics is going to be there in some aspect to award us our Special Olympics banner. So it's going to be a good day for sure. And I know it's flurrying this morning. It might be a little on the chilly side, but mid-40s, not like it's been the last couple of days. So, but I think the snow is going to hold it off for us, so that's good. So come out if you can. 5 o'clock at the baseball field here at Ponderosa. That'd be awesome. Okay, we did it yesterday. It was amazing. We learned the shortcut. What was it again? How do we do it? Page 130, I guess, is kind of a good place to pick stuff up where we left off. What was that really nice shortcut that we saw for all these? Do you remember? Here, I'll start with this one. This is a recap. F prime of x. This is what we did yesterday. 0, just for good measure, minus 9x squared plus 24x cubed. Well, I mean, the derivative of a constant is always just going to be 0, right? So that kind of exists on its own, regardless of whatever this rule is. Okay, the derivative of a constant is always 0, but what about the other two? How do we do it? I'll do another one. Prime of x, 2x to the negative 2 minus 6x to the negative 2. What is happening every time? So say it again. Okay, so every single time we're going to drop the exponent down by 1. Okay, so like 3 became a 2, 4 became a 3, negative 1 becomes a negative 2, definitely getting smaller. Okay, good. Even 2/3, right? 2/3 minus 1, yeah, negative 1/3, good. Definitely that. Exponents get decreased by 1. But there's also something else that happens. What else is happening along the way? I know you were virtual for this yesterday, so I know it's less, not as easy to remember, I guess. Maybe somebody at home could speak up if they remember what our little shortcut is. Maj, what do you think?
Multiply the number from the exponent.
There we go. So we take the original constant and the original exponent, we multiply them together out in front. So like this negative 3 and that 3 right there get multiplied together, and that's my new coefficient. 6 times 4 is 24. Good. And that's it. Those are only the 2 things you have to do. You take the original coefficient multiplied by the exponent, and then you just decrease the exponent by 1. Now, any constant is just 0. So eventually, I'm not even going to write this. Like, that's just going to go away. I'm just going to say, okay, 9 minus 9x squared. And if it's just linear, right, if it's just 3x, then it's just the slope, because that's all we're looking for is slope. But if we do have exponents that we want to keep track of, we'll multiply that with the coefficient and then decrease the exponent by 1. Okay. Now, what I wanted to do here at the bottom of page 130 is to kind of formalize that and like give us something that we can look back at. And so I'm going to talk about this notation here in a second, but I'm going to come off on the side first and kind of make it really, really nice to talk about what's called the power rule. Okay, that's kind of our fancy name for it. That if f of x is some polynomial looking thing, so some c times x to the n. Okay, and here's what's really nice. We just go one term at a time. We don't try to do the whole function all at once. Just gonna look at one term and then the next and the next and then the next and see how many we have. And I apply the same rule every time. And so it could have a bunch of them, but we just do one at a time, doesn't matter. If that's true, then here's our derivative, f prime of x, okay? Whatever the constant, whatever that coefficient is out front, we take that number and we multiply it by the exponent. So we have like this c times n. Now, if n is 1, it doesn't change, right? And so that's why we just take the slope. And of course, we have the original rule that if it's just, if x equals 3 or 5 or -1 or whatever, the derivative is 0. Okay. But if we do have a power, right, that we want to kind of keep track of, we're going to multiply those together, and then we'll just decrease the exponent by 1. Okay. So c times n times x to the n minus 1. And it all goes back to how the limit definition worked out that way. And we could look back at all the ones that we did, and you'd see that that's always true. We now have the shortcut that's kind of worked all the way through. And it just goes back to binomial expansion, and we're really looking at the second term in binomial expansion, the only one that just has an h, right? Because the first one was just x cubed or x to the 4th or x to the 5th, right? The second one had x one less than that. It was one less. We moved the exponents down one, move them up one, and we just had that h, and then we factored it out, divided it away, and it all kind of works out that way. Okay, and there it is. That's the power rule. Voila. Okay, and you just do that for every single term, every single time. Okay, but it has to be written really nicely. Just kind of one term plus another plus another. No parentheses. No fractions for with x's on the bottom. We want to make sure that it's written like that, right? It's c times x. Okay. Now over to the right here is just another type of notation for derivatives. Okay. And it all comes back to the idea that slope was the change in y over the change in x, right? The derivative is always just the slope of the tangent line. And so, what's that letter again right there? The delta, right? What's the first word in the word delta? Okay. And so what we're going to do is we're kind of separating the change from everything else. That what's really going on here, and whether you call it y or you call it f of x, doesn't matter. We are kind of separating the, just like the operation, you could call it the operator that's happening to the function. We're going to find the derivative, which is really just the change in y or the change in x. But that delta is disappearing, right? We're getting so close together, our points are getting closer and closer together, that we actually change it from a delta to just a d, okay? You can actually read this out loud in a couple different ways, okay? The derivative of whatever. The derivative of, and f of x, of y, of x to the n, whatever you want, okay? And that's this. That's that right there, okay? And so, yeah, it's delta y over delta x, but we get some language that kind of makes even more sense for us, given that we're talking about derivative. The derivative of, in this case, it would be x to the n. And then this bottom part down here, this dx, okay, is actually read out loud as, that's close enough, with respect The derivative of whatever with respect to x. Now, the reason why we have that dx part down there is because maybe our input's x, but maybe it's t. And so I would have d dt. Or maybe our independent variable is an m. Okay, then we have ddm, whatever it is. Okay. So the derivative of, and a lot of times that's just y. We can just say y or f of x or something like that. And we'll even put it up here, right? We could say, you know, we could go like that, which for us is just going to be dy dx. Okay. And I just kind of said it in passing. You can read it out loud just by reading the letter. Okay. We could read all of this as d dx. But really, it means the derivative of whatever with respect to it. Okay. And as that variable changes, we'll just keep it, right? ddt, dda, ddb, ddc, whatever it is. But you can say it out loud just like that. And even this right here, this is probably the most common version. I would literally just say dy dx. You can say dy over dx, but I'll tell you what, technically, it's not division. It's not a fraction, but we treat it like one to allow us to deal with differential equations and stuff when you get to like Calc 3, 4. But we even start to look at diffeqs, differential equations that have the derivative in it, differential difference. But we just call them diffeqs. But I'm getting ahead of myself a little bit. Just some nice notation. But that derivative is nx to the n minus 1. Right? Drop the x one in front. Multiply it through by whatever constant's there. Well, if there is no constant, then it's really just a 1, right? And we'll decrease it. And what I wanted to give us a chance to do before we get to page 131 and they start messing with some really hard ones at first that don't always look the way that we want, we kind of have to rewrite them. I wanted to give us a chance to try some power rule ones that are just ready to go. Okay. And so as much as I want to stick in the textbook a lot, I find that sometimes it's just, or in the guided notes a lot, I find that's just not enough sometimes. And so last night, this morning, I just kind of made what I'm calling really quickly just a homework 2.3. I just want you to try these 5 like right now. Call it homework 2.3. We can put it up on Canvas, give you some credit for it. But I want you to just like take a look at these 5 functions. I'm actually going to change the name of this last one. I'm just going to call it y equals instead. Huh? I know. And you can do it separately somewhere that's convenient for you. Okay. I don't know that there's a whole lot of empty space in that guided notes for you to do that. And of course, folks on campus, this is folks at home, this is sitting on campus for you. But just make sure you can do it. Okay. And what we want to try to do is write the simplest version of whatever that is. Okay. But first things first, let's see if we can use the power rule. And I'll get to the same answer in one step. The derivative can now be found in one step. Okay, by just applying the power rule, because every single one of these is ready to go. There's no parentheses. There's no rational functions. There's no radicals. Everything is coefficient x exponent plus coefficient x exponent plus coefficient x exponent, whatever it might be. Okay. Take a couple minutes. Make sure that you're writing down the original function, not just the derivative, so we can go back to it and look at it and see, oh, if you made some mistakes, where did the mistakes happen? Or if you did it right, you have a really good guide to use in the future. Okay, so try the derivative of all of these. And you can use Newton's notation with the f prime stuff. What we just learned is Leibniz's notation with that dy dx dx. Give it a shot. Give it a shot. And then put it on camera. When you're ready. When you're ready. Now, so all of your work is just going to start off with f prime of x equals g prime of x equals, and so on. Jumping right to the derivative. Let's see how we do. Figure you guys here. Use the power rule. Yeah, please. There's a spot on Canvas 1 2.3. Take pictures to put it up there. Quick, easy 5-point day. And it looks like we won't be finishing chapter 2 before spring break. Okay. So, and that's okay. We will just pick it up where we left off. But we will finish it the week after. I don't want to rush through the end of chapter 2. It would be so silly. Yeah. Of this week? Now you don't have to worry about it. Now there's nothing that I need to hand to you or give to you. I think so, yeah. We'll see how far we get today on our slightly shorter day. I wanted to get to sine and cosine today. But you'll see that we'll start to really put the pieces together and say, okay, like here's this function. Let's find the derivative. Let's find all the horizontal lines. Let's figure out where it's increasing and where it's decreasing. And then, okay, where is the relative max? Where is the relative min? Kind of looking at the derivative on either side and trying to get this kind of feeling from the function. And putting all those pieces together. That's what we'll start. All right, some solutions. Oh, that's wrong. Good start. Okay, no need for the plus 0. I put it there just so that we can see it. But anytime you take the derivative of a constant, so that derivative of 1, right? Because we're just going to take the derivative of 3x squared, the derivative of negative 5x, and the derivative of 1 separately, which is so nice. So I just do each one. Through 3x squared, nice. Take the 2, drop it in front, multiply it with the 3, decrease the exponent by 1. Now the derivative of negative 5x, that's just linear, so I just take the slope of that line, which is negative 5. Now, I mean, it still works. Yeah, there's like a 1 right here, and you multiply it with it, and you decrease the exponent by 1, it becomes a 0. But do not think of like 1 as 1x to the 0 and try to like waste all of that time. I mean, it's still going to work. Like take the 0, multiply it by 1, it becomes 0 anyway. But if you just remember that it's the derivative of a constant, it's always going to be 0. Then you just go. But the algorithm works no matter what, which is super, super nice. Anybody wants to use a limit definition on number 3, you go right ahead. You expand x plus h to the 5th and x plus h to the 4th in one problem. No thanks. All about the power rule. So nice. Decrease by 1, the negative numbers are going to get more negative. Be careful there. And just watch your signs to make sure you're multiplying things together. And if you're not great with fractions, then break out a calculator and do 1/3 minus 1 and get -2. Okay? But being comfortable with fractions and just all we have to do is subtract 1. So really in my mind, I'm doing like 3/2 minus 2/2. Right? 3/2 minus 2/2, because that's just 1. And 1/3 minus 3/3, because that's just 1. How did we do? Crushed it? Sweet. Put it on canvas so you don't forget. Go ahead and do that now, once you're ready. And then we can start to challenge ourselves a little bit more with slightly more complicated setups to start. But all of them that we're going to look at today can be written like these. Now, whether they look like 1 or they look like 2 or 3, whether they look like 4 or they look like 5, kind of depends on what that original setup is. Because here's the thing. I don't love the way that number 4, either the function or the derivative is written. Not that it's wrong, but that's not what our original setups will probably look like, and it's definitely not how our final answers are going to be. What do you think it is about number 4 that kind of just irks me a little bit about its setup? What do you mean? What do you mean? So it's not in standard form, you mean, because like the biggest exponent isn't first? You're absolutely right. The biggest exponent a of x is -1, because that's furthest to the right on the number line. I know it's kind of weird to say -1 is bigger than -2, but when we talk about big versus small, it's where are they on the number line, which one's bigger? Absolutely. That's one thing. But we don't sometimes have control as to what order they write it in. And usually I'll just kind of say, all right, if that's the order you're going to write it in, then I will bite the bullet and not worry too much about it. But you're right. I don't love that it's not written biggest exponent on down like the way that we like. There's also something else I don't love about it. Negative exponents. Okay. We don't like to start with negative exponents, and we certainly are not going to end with negative exponents. Okay. And so what we're going to need to do for something like a prime of x, even y prime, right, our answers there, is we want to make sure that we change all of our answers so that there are no negative exponents left behind. And so what I'm going to do is I'm actually going to take a second here. I'm going to erase y prime just for a second. We'll come back to that. And we are going to rewrite a prime so it looks better. Okay. Now, negative exponents just means rational, right? Move that base, whatever's being raised to the negative power, has to move its position from the top of a fraction down to the bottom, or vice versa. Okay? So when I change -6x to the -4, tell me, what is being raised to the -4th power? Just x. If we wanted the coefficient as well, it would look like this. If we wanted that -6 raised to the power, it would look like that, but it doesn't. Okay? And so what that means for us is we can't. Why is it only? We can't move the -6, okay? We're going to create a fraction where that -6 remains on top, and the x is going to move down to the bottom. And when we make that switch, the exponent becomes positive. Okay, so those two things kind of stacked right on top of each other are equivalent to the same thing, but you're going to see that they're always going to ask us to write our final answers with non-negative exponents as often as we can. Okay, so same thing with this, right? The 2 isn't being raised, so the 2 doesn't move. It's the x that's going to move to the bottom and become a +3 instead of a negative. Okay, now that -6, like the negative could exist on top, or you could drop it out in front. And you're going to see me do that right now, negative, so -5. Cool. All right, so this is just a better version of A prime. Absolutely. Now, the other thing that sometimes they'll have us do is they'll have us combine fractions together too. So we'd have to like create common denominators and kind of go from there. But I'm good right now with just that. Absolutely. So we got some things we want to talk about there. Now, this is kind of up to the person writing the question. Sometimes fractional exponents are just fine. We can just leave them like that. Sometimes they like us to rewrite them in radical form. And so we're going to have a conversation about kind of both of those setups. But for sure, what I can definitely do is we can take this negative exponent and do the same thing that we just did, right? I can call this 3/2 x to the 1/2. That one's fine, right? And then minus 2 over x to the 2/3. 2 over x to the 2/3. But fractional exponents are power over root, right? Number on top is the exponent. Number on bottom is the index. That's the root for the problem. And so we might find ourselves doing, as we get more comfortable with it, honestly, I think a lot of calculus teachers would say, hey, that's good right there because what you're about to do is the exact same thing. But let's see it. Okay. 3/2 is my coefficient. That doesn't change at all. It doesn't go anywhere. But x to the 1/2, like what does that really mean? Huh? Square root, right? Power over root, a power of 1 and a root of 2. So it's like there's this 2 right here and this 1 right here for that 1/2. Of course, we don't need either of those. Raising something to the first power. And the smallest root I can take is 2 anyway. Hi there. Sure. Can I get her?
You can have her come down as soon as possible.
Perfect. Thank you.
Thank you.
And then minus 2 over. All right, so that's a 2/3 in there. I know it's a little jumbled. But a power of 2/3. Okay, so an exponent of 2/3. So it's got a power of 2 and a root of 3. And we need kind of the opportunity to write that in radical form by separating those two and saying, all right, I've got a cube root, because that's the number on the bottom, so there's my root. But underneath is not just x, it's x squared. Okay. Now, it all depends on what they ask of us in terms of what our final answers need to look like. I'll tell you right now, I've never seen a question that said it's okay to leave negative exponents. They always want us to get rid of negative exponents. But writing it in rational exponent form versus writing it in radical form, that's just kind of up in the air as to what they want to do. But either of those two last lines down there, I think are great. Okay, I'm happy with either one. But if I specify radical form, then you know where we're going to be coming from. And the issue that I have is that if it starts like this, then I can certainly end that way. Okay, this is a fine way to start, so I'm okay ending that way. If it starts with roots and stuff kind of built into the problem, I'll probably take that extra step and get there. Okay, but the thing that I also want you to remember is that this is a perfectly acceptable way. In fact, it's better notation to write your derivatives, especially when they're y equals, as the derivative of y with respect to x. Okay, the derivative of y with respect to x, also known as dy dx. I don't even say over. Dy dx. It is a notation that is not really division. It's not a fraction. It's notation that looks like a fraction. But when we get further along, we're actually going to use it like a fraction to break things apart and have a dy over here, and then we're going to multiply by dx. But it is just kind of based on that notation. And that's Leibniz. Okay, that's our boy Gottfried that had a really, really good idea. And that changed the game big time. Okay, that changed the game. Feeling okay with power rule? Okay, so now let's jump back into the actual guided notes themselves, because what you're going to see when we turn to page 131, so go ahead and do that, turn to 131. And look at the instructions at the top. Okay, find f prime for each of the following functions. Look what and they specify what they want. Leave your answers with no negative exponents. And they even say no rational exponents, right? So we would have to make the switch to radical form with the roots and all that stuff. And they even say, listen, if you've got like a bunch of rational expressions all being added or subtracted together, combine them into a single one. Okay, and so we'll take a look at what that looks like. But look at this first one, top left. That is not ready to go yet. That is not coefficient x exponent plus coefficient x exponent plus coefficient. It's not written the way we want. And so what we're going to have to do first is rewrite the function before we even get to the derivative. I cannot find the derivative using the power rule if it's not set up like a polynomial. And so we're going to have to rewrite one or more of these terms as we go in order to use the power rule. And so take a look at that first part of that first function, the 2 over x squared. What we're going to have to be comfortable doing is rewriting that coefficient x exponent. Then we can use the power rule, and then we'll switch it back. So rewrite this without the fraction. What does that look like? Good. 2x to the negative. Right? Now, what about the minus 4x cubed? Does that look good? Are we okay with that term? Okay. So we don't change everything sometimes. Maybe they'll just make us change one of them. So there's the function. Now I'm ready to find the derivative. Once it looks the way I want, then I can jump in and go for it. And because it looks like a polynomial, then I can just use the power rule. Drop the exponent in front, multiply it with the coefficient. So negative 4, right? 2 times negative 2. X, and then decrease the exponent by 1. If it starts negative, it's going to get increasingly negative, right? Negative. And then we do it again for the next one. Minus 12 x. But they were pretty clear that that negative exponent is no good. Go on. And so we need to rewrite that blue expression there so it doesn't have negative exponents anymore. And just like we made the switch with the function to make negative exponents, now we just go back the other way and say, all right, I'm going to keep the negative out front. So I'm going to do negative 4 over x. Right, the only thing being raised at negative power is the x. That's the only thing that moves. And if it had parentheses, we couldn't use the power rule anyway. We'd have to expand first. Okay, no parentheses. But the negative 12x squared looks good. I like it. Negative 12. Okay, no negative exponents and no rational ones. That's good. Now, the last thing that they want us to try to do is to try to write things as like one single rational function. That if you have a rational piece, then we can put this whole thing together and make one rational function. Okay? And all we need to do is just make a common denominator and put them together. Now, the only denominator is an x cubed, so there's my common denominator. Right? Whatever your biggest exponent of x is, that's going to be your common denominator. And so really all I have to do is make this fraction also over x cubed, and then we'll combine them together. Let's do that all in one shot. The negative 4 is good from that first fraction. But if I wanted to create this right here to be a fraction over x to the third, right, create common denominators, you multiply top and bottom by whatever you need to. And so what's going to happen here with this negative 12x squared term is we're going to take all of this right here and we're going to multiply top and bottom by that fraction, right, by that x thing. And so it just becomes minus 12x. Now, I think in general that is probably going to cause us more problems than we might like, trying to put things together like that. But it is something that they want us to get better at. Okay. For me, this part is the least important part of all this. It's the negative exponents, the rational exponents, trying to make sure that we can. Okay. Let's try this next one. This one is not ready to go yet. We got to figure out a way to rewrite this function so it is not with that negative exponent, or with that, I mean, it is a negative exponent on the bottom. I got to get rid of the fraction. And so what do you think we could do to write f of x? That's all divided by x is, right? Is divide each one by x. You have a single denominator. Okay, sweet. Let's call this 3x to the third minus 3x minus 2. Dividing each one by that denominator. And you're going to see that in this unit, that's the only kind of thing we can do with fractions. If that was an x plus 1 or a 2x minus 3, or if it's a binomial, we are in trouble. Now, we cannot divide it quite so nicely. But just a single denominator, yeah, just divide everything by that. Again, that's not the derivative. That's the function still. Now it's up to us to find the derivative. Okay, so rewrite your function if you have to, and then jump in and use the power rule. Okay? Now, this is the function that I'm going to work with. It's the same thing. Now I take the derivative, drop the exponent in front, multiply together, decrease the exponent by 1. Linear, so I just take the slope, constant. And I'm done. All right. I'm done there, and I'm done there. Because when I had to take this negative 12x squared and create a common denominator so I could make a single rational function, I had to multiply top and bottom by whatever the denominator was that I was trying to get to, which was x cubed. Yeah, so I multiply top and bottom by x to the third. And you can kind of see, like, just like your same thought process of, hey, like, let's divide each one and I can get the same kind of function. Look, divide this by that. Wait, divide this by that x to the third. Let me get back here. So you know you did it right. I don't love that we have to do that next step, but that does happen sometimes where they ask us to make one nice big one. Cool. All right, last couple. This is not ready to go. Not even close. I need coefficient x exponent plus coefficient x exponent. I cannot have parentheses. I cannot have this product written like this and find the derivative with what we know so far. Chapter 3, I will show you how to do that without changing the function. But you might find that it's almost the same amount of work depending on what you do, especially if there's 3. If there's 2, product rule actually might be a little bit faster. But right now, we don't know anything like that. What we have is the power rule. So what we're going to have to figure out is how to rewrite to this one. Now, it comes down to how do I multiply 3 things together? And so don't write this down, but just kind of look at it for a second. What is the thought process you have in multiplying 2 times 3 times 4? What do you do first? 2 times 3, and then you stop, right? You see what you get. So what do you get? What's 2 times 3? Okay, so you get a 6. Then what do you do with it? 6 times 4, and you keep going, right? So you multiply like 2 things together only, see what you get, and then you do the product with the rest of that, right? I can't do it all at once. But what I can do is take these first 2, multiply them together, and see what I get. Now let's kind of bring that 2x plus 1 with me for now. That's kind of like that 4 waiting there for me to do 2 times 3. Okay? So multiply out what's inside there and simplify while you're at it. All right, x squared plus 2x plus 3x plus 6. So x squared plus 5x plus 6. Again, this is just the function. This is not the derivative yet. Now we'll multiply that. So go ahead, give it a shot. See if you can distribute well enough to get yourself to the simplest version of this answer. And hopefully you got it. Then we can find it. Once you get to there, man, this derivative is easy. And it's amazing how fast we can go. Question? 2x cubed. Now I've got a 1x squared and a 10x squared. So that gives me 11x squared. Then I got a 5x and a 12x. That got me 17. So I think I'm good.
I accidentally typed for you too at the beginning.
Ah, okay. There you go.
That's why I was
Gotcha. Cool. All right, let's do one more, and then we'll kind of call it. Okay, and then we'll pick this up tomorrow where we left off. We got to rewrite f of x. Absolutely, got to rewrite this function first. And just like we did on the last one, that Ethan said, just divide by whatever that denominator is. I think it's a great idea. But when we do that division, I'm taking away more x's than I've got. And so in your mind, what I think should be happening is this. Kind of realizing that with a single denominator, you can break the fraction apart into as many pieces as there are, which will then get us to a much nicer version of this function. Give me like 30 seconds, right? What's the shortcut with exponents when we divide? What do I do with the 3 and the 5? Subtract them. 3 minus 5 is negative. Right? Minus 5, x to the negative third. That's f of x. And so if your denominator's degree is larger than the degree of the terms that you have on top, your function's going to have some negative exponents in it right now. And that's easier for us in the middle of the problem. Okay? I don't mind. In fact, I prefer that I deal with exponents, whatever they are, as I work. I'll deal with the fraction once I get there, but now I can very easily find this derivative. Negative 2x to the negative third plus 15x to the negative fourth. And then we'll make the switch back. Okay, and so we will pick it up right there tomorrow, and we'll figure out how are we going to rewrite that without negative exponents and as a single rational function. Yay, see y'all. Thanks, everybody. Make sure you get that homework 2.3 submitted and let me get some credit.
Will there be any other like homework that
Probably not. No, probably not. I think what I want to do in these next couple days is finish those, like finish that one and do the last two. And then you'll see that the next page is sine and cosine derivatives. I know they're really fun and super awesome. They're actually